let's get right into it. At the very heart of robotics, there's this one fundamental question. How does a machine get from point A to point B without, smashing into everything? It's the one challenge you have to solve to turn a hunk of metal and wires into something that can actually navigate our world on its own. I mean, think about it. You've probably got one of these at home. How does that little robot vacuum get right to the edge of the stairs and just stop? It seems like magic, right? Well, it's not. It's actually this brilliant step-by-step process of seeing, mapping, and planning. And that's exactly the puzzle we're going to piece together today. We're going to follow a robot's whole learning process. First up, how it even sees the world in the first place. Then, how it takes what it sees and draws a useful map. After that, we'll see how it finds the absolute best route. And finally, the really tricky stuff. How it handles surprises, like new places or, people walking in front of it. Okay, so before a robot can even think about moving, it has to translate our messy, complicated world into a language it can actually process. And the way it does that is by turning everything into a giant, simplified connect-the-dots puzzle. And the tool for that comes from mathematics. It's called graph theory. The building blocks here are super simple. All you have are vertices, which are basically just the dots or specific spots in a room. And then you have edges, which are the lines or the safe paths that connect those dots. That's it. Every single map a robot uses, whether it's on Mars or just cleaning your living room, starts with just these simple dots and lines. And you can see how these simple rules can build different kinds of worlds for the robot. Over on the left, that undirected graph, that's just like a normal street. You can go from point A to C, and you can go right back from C to A. But on the right, you've got a directed graph. Think of that like a one-way street, which is absolutely crucial for something like a factory robot that can only move forward on an assembly line. And this is where it all pays off. With this really simple language, a robot can suddenly grasp some pretty complex ideas. A warehouse bot, for example, can follow what's called a cycle, a loop that takes it from the loading dock to the shelves to the charging station and back again. And maybe most importantly, it can answer the fundamental question, can I even get to my goal from where I am right now? So how do we put this into a real room? Well, the most popular way is to just imagine a virtual grid laid out over the floor. Each little square is a node, a dot. From the square it's in, the robot can move to its 4 direct neighbors, up, down, left, right, or if you want to get a bit fancier, all 8 neighbors, including the diagonals. It's a simple idea, but it's incredibly powerful. Okay, so the robot sees the world as a grid of dots. But which of those dots are actually safe to travel on? Now we've got to draw the map itself. And it turns out there are a few different schools of thought on how to do this. Each one has its own strengths and weaknesses. So the first strategy is all about one thing: speed. We want the absolute shortest path possible, no exceptions. The best way to think about this is to imagine taking a rubber band and stretching it from your start point to your goal, making sure it has to go around all the obstacles. It'll naturally snap into place along the tightest, most direct route. This method is called a visibility graph. What it does is connect all the corners of the obstacles that can see each other with a straight line. The path you get, which you can see in blue, is mathematically the shortest one. But look closely. It scrapes right past the corners. It's fast for sure, but it's also pretty risky. Not a lot of room for error. But what if you don't care about being the fastest? What if safety is priority number 1? Well, then you use the complete opposite approach. This strategy is designed to keep the robot as far away from danger as it can possibly get. Like when you walk down the exact center of a hallway just to make sure you don't bump into either wall. And this is what that looks like. It's called a Generalized Voronoi diagram, or GVD for short. Just look at those blue lines. Every single point on those lines is the exact same distance from the 2 nearest obstacles. This creates a whole network of paths that are maximally safe. Yeah, they might be longer, but if you're a robot carrying fragile cargo, that extra margin for error is everything. And there are other cool ways to do this too. On the left, you've got something called cell decompositions, which just breaks up the free space into simple shapes, and the robot just kind of hops from one cell to the next. And on the right, the watershed algorithm imagines the map as a 3D landscape, where obstacles are deep pits, and the safest paths are the high ridges between them. Pretty clever stuff. So, the robot has its map. It knows where it can and can't go. Now we're at the main event. How does it actually search that map to find the single best route from its start to its goal without wasting a ton of time wandering around? Well, the most basic way is what's called a blind search. On the left, depth first search just picks a path and goes as deep as it can until it hits a wall. Then it backtracks and tries again. On the right, breadth first search is more cautious. It expands outward like ripples in a pond. But here's the key.
Neither of them has any idea where the goal is. They're just blindly exploring, which can be super inefficient.
This is where things get really, really cool. Instead of just wandering aimlessly, what if the robot could use a hint? What if it had an educated guess to help guide its search in the right direction?
And that hint, it's all captured in this one beautiful little formula. This is the A-star search algorithm. That's A-star, and it is, without a doubt, the king of pathfinding. This simple equation powers everything from bad guys in video games to the GPS in your phone.
So let's break it down, because it's actually pretty simple. G of n is the past. It's the actual cost of the path you've already traveled from the start. H of n is the future. It's a guess, what we call a heuristic, of how far it is from where you are now to the goal. A really common way to guess is just the straight line distance, as the crow flies. And F of n is just the total. You add the past and the future together to get your best guess for the whole path.
So, by always choosing to explore the next step that has the lowest total estimated cost, the lowest F value, A-star intelligently pulls itself towards the goal. You can see on this grid, it never even bothers exploring those squares in the top or bottom left because its guess, that H value, tells it, hey, that's the wrong way. It just zooms around the obstacle and finds the best path super efficiently. Now, everything we've talked about assumes the robot has a perfect map of its world. But what happens when it doesn't? What if you drop it into a brand new place it's never seen before? How does it get around when it's basically flying blind? Well, there are some pretty brilliant tricks for this. On the left, you've got what's affectionately called the lost cow problem. Imagine you need to find a gate in a super long fence. You go 1 step left, then 2 steps right, then 4 left, then 8 right. This doubling back and forth pattern is a provably efficient way to find something when you don't know where it is. And on the right, a simple robot with a laser can just look for gaps, like a doorway, and head for them. It's a really robust way to explore without needing a formal map at all. All right, time for our final and probably the toughest challenge. What does a robot do when the obstacles themselves are moving? How does it navigate a crowded sidewalk or a busy highway where everything is constantly changing? Trying to replan the whole route every millisecond is just way too slow. So instead, robots use this amazing reactive trick called velocity obstacles. So looking at this picture, Robot A doesn't just see Robot B, it calculates what's called a cone of collision. That's what all that math is about. This cone represents every possible speed and direction that would cause a crash. So to stay safe, all Robot A has to do is pick a velocity for itself, any arrow that's outside that cone. It's a lightning-fast, elegant way to dodge things on the fly. So, let's just recap the whole journey. The robot starts by seeing our complex world as a simple connect-the-dots graph. Then it draws a map of all the safe paths, deciding between the fastest route or the safest one. Next, it uses a smart search like A-star to find the absolute best path on that map. And finally, it uses clever tricks to adapt when the map is a total mystery or when the world just won't stand still. From a vacuum cleaner that doesn't fall down the stairs to a rover exploring another planet, these are the fundamental ideas that allow machines to move through our world. And it really leaves you with a pretty mind-bending question. Once robots have totally mastered moving through our physical spaces, what other kinds of complex, abstract worlds will they learn to navigate next?